Good morning. My name is Eric Popp. I'm with the Electrical Engineering Department here, as well as with the Precourt Institute for Energy, PIE at Stanford. I've actually made paper copies of these slides, and Chris Newman was nice enough to bring them from the office and pass them around, so you can actually thumb through ahead of them. We will also have the PDF of the presentation posted online later on, but we don't have it right now, so hopefully the paper copies are going to be just good. They seem to have come out good. All right. So Richard Sassoon invited me to this to give this seminar, this tutorial really, and he told me that I should talk about sort of the history. I should talk about a little bit about the physics of thermoelectrics, and we also agreed that I would talk a little bit about the application of thermoelectrics. So you'll see that basically the talk is roughly split between these three areas. Actually, the last part, final remarks, is a little bit also more of a selfish point of view, some of the things that my group has worked on over the last few years. So I want to start with the fundamentals of thermoelectrics, and then of course we'll move on to applications and so on. So of course, you know, one of the first things when you sort of do a tutorial 101 type presentation, right? One of the first things that you need to do is you need to look up the term in the dictionary. And I wasn't very happy with a lot of dictionary definitions I found, and I'm actually not completely happy with the one from Google either. But this is what Google actually puts out when you put the word thermoelectric in it. The reason I'm not happy with it is because it says producing electricity by a difference of temperature. So that's actually only the Seebeck effect, but that's not describing the Peltier effect. So it's really actually the reversibility between producing electricity and producing temperature. So it's really the two of them are actually reversible in this case. But anyway, what I did like from Google is that it actually gave me kind of a timeline of the usage of the term, which really nicely maps with the discovery as well as some of the major advances in this field. So the discovery of thermoelectrics, and probably the first time the term was really used, is around 1821. Thomas Seebeck discovered the effect in 1821. He actually thought it was something else. He thought it was thermomagnetism, it turns out, but actually it was thermoelectricity. That was clarified 2 years later. The Peltier effect, which is the opposite effect of the Seebeck effect, was discovered a few years later. But it took about 100 years, if you notice, 100 years from discovery until basically the first commercial thermoelectric generators, as far as I'm aware, based on what I've been reading. Things really took off after the Second World War, and you can really see it in the usage of the word in the English language. Things really took off after the Second World War, after essentially the discovery of semiconductor thermoelectrics, specifically bismuth tellurium, which will show up a number of times in our talk. And then the space race and all the Cold War was basically all this stuff right here in the 1960s, 70s, and so on. And a lot of space applications and remote sort of power generation applications, which I'll describe a little bit later. All right. So, just start with the beginning. So the Seebeck effect, 1821. This is the only picture I could find of Thomas Seebeck. Looks like a very pensive man. But this is another picture I found essentially of his experiment. So essentially what he did is he connected copper and bismuth wires, which is basically what today we call a thermocouple. We just connect two metal wires, right? And he noticed that heating one end, right, with a candle, let's say, right, he was able to deflect a magnetic needle nearby, right? So they didn't know too much about the interchangeability of electricity and magnetism back in the 1820s. So at first he called it thermomagnetism. A little bit later, 2 years later, in fact, Ørsted actually correctly explained that this electric flow was actually due to a temperature gradient. So there's a temperature gradient that sets up an electric current flow inside this thermocouple, right? So basically, the very, very simple expression for this is you basically get a voltage developed in an open circuit. You get a voltage developed when you have a difference between the Seebeck coefficients of these two materials, material A, material B, in this case, copper and bismuth. And you have a temperature gradient between points, I guess, T1 and T2 over there, right? So and of course, if you close the circuit and you have some sort of external resistance, you're actually going to get current flow. And so that's going to deflect the magnetic needle nearby, right? The Seebeck coefficients, for now, we're going to get a little bit more detail about them, but the Seebeck coefficients are basically, they're also known as thermal power. So I use the two terms interchangeably. And they're basically a coefficient that's very specific to that particular material. It's maybe something like, you can think of it as the electrical conductivity, but it's really a different type of property of the material. It's a function of temperature. It's a function of doping, if you're talking about semiconductors, and a few other things, as we'll see. Just to pick some numbers, I think numbers are very important if we're going to talk about practical applications. To pick some numbers, a typical Seebeck coefficient is on the order of 300 microvolts per Kelvin. let's pick a temperature difference of 100 Kelvin. So that's basically assuming one end of the thermocouple is stuck in freezing water and the other one in boiling water, right? We generate about 30 millivolts of voltage, right? If I did the math correctly, right? So then the question is, okay, 30 millivolts doesn't sound like a lot of voltage, right? What if I actually want to generate using heat? What if I want to generate the voltage of a simple AA battery, right? How do we do that? So the answer is, actually, does somebody know the answer? Or is it too early to, what's that? Run them in series. Okay, that's right. I wasn't sure if it's too early to ask questions or not. Okay, so, okay, warming up. So basically, we'd actually have to put about 50 of these in series to generate 1.5 volts, basically like a simple battery, right? Okay. The Peltier effect was essentially discovered a bit later. The Peltier effect is the opposite of the Seebeck effect, right? And basically what this means is that if I actually run a current flow through a junction, so this time I'm forcing current, electrical current, I'm forcing it through a junction of these two materials A and B, I can actually use it to heat or to cool that particular junction. The very simple formula is basically the heating power right there is a function of the difference in Seebeck coefficients between the two materials, the temperature, and then I is the current that is actually flowing through this entire very, very simple, essentially still a thermocouple, basically, the way it's shown over there, right? A really important thing, and I'm going to try to occasionally make use of my little pen over here. A really important thing is this, is that the heating and cooling are actually reversible, right? So this is not an irreversible process. This is not, once you do it, you cannot undo it. You can actually really reverse this thing, right? In fact, you can even reverse the sign of the current I, and you can actually get heating or cooling in these little junctions, right? Again, to pick some numbers, since I like numbers as an engineer, to pick some numbers, assuming a simple current of 1 milliamp, again, a delta Seebeck of about 0.3 millivolts per Kelvin, and room temperature, right? Basically, it gives us a power of 90 microwatts. This is the power of heating or cooling of such a junction, 90 microwatts. Again, how do we generate greater cooling or heating power? We basically have to put a whole bunch of these, together. We have to string them together so we don't just rely on one single junction, of course. Right? Okay. So, just looking ahead a little bit, trying to answer this looking ahead, if you look ahead, basically the commercial thermoelectric modules today are typically arranged in a series of alternating what's called N-type and P-type doped semiconductor legs, because this actually turns out to give us the largest Seebeck coefficient difference. And the way they're connected is what's called electrically in series, yet thermally in parallel, right? So right here you see these, this is actually the module itself, and you can actually, the zoom in, you can see these things. So there's, these are the connections. The current basically will flow like that, right, through these legs. So it'll flow up into the red leg, down into the green, up in red, down in green, and so on. And it will sort of snake around. And so the heat will actually be removed, right, from the top junction and then basically moved down here at the bottom junctions of these things, right? And of course, the current will just be one connector for the current going in and one connector for the current coming out. Speaking of which, I actually have a little thermoelectric module here that I'm going to pass around. So it's literally, this is just a cheap commercial thermoelectric module, which has been actually, disassembled enough that you can actually see the individual P and N legs in it. So I'm going to pass this around, and it looks exactly like that. It looks, you can buy this at most electronic supply stores, and it looks pretty much like what's shown on the screen. Okay. All right. So there's another component, I guess, of thermoelectrics, also known as the Thomson effect. Now, Thomson is William Thomson, also known as Lorentz Kelvin. And in 1851, Thomson basically realized that, wait a second, you can actually, thank you so much, you can actually generate heat within a material continuously without actually needing a junction. This is a very, very subtle difference, right? So he basically realized, this is the key word here is continuous, okay? And there's a gradual change in the Seebeck coefficient due to a temperature variation inside the material, right? So you can have a material, the material is not going to be necessarily at a uniform temperature. If you have a temperature gradient across the material, you generate a gradient in Seebeck coefficient, which in turn generates a local electric field and then generates local heating or cooling, in addition to whatever joule heating or cooling might be happening in the material at the same time, right? And again, the mathematical equations are shown over here. The electric field that's generated is just temperature multiplied by the gradient in the Seebeck coefficient that is generated by a change in temperature along this material. Maybe the way I would draw this is, if I drew temperature as a function of position in my material, right, it would look something like this, and there would be a slope, right? So that generates a non-zero temperature gradient, and that's essentially what we're seeing over there. Temperature gradient generates a Seebeck coefficient gradient, and that's basically it. The Thomson effect turns out to be directly measurable in a single material. On the other hand, if you want to measure precisely Peltier and Seebeck coefficients, you really need pairs of materials, in other words, material junctions. Those of you that came in a little bit late, I think there are handouts somewhere around the room, and I do think we have enough handouts because I prepared. Does somebody know where the handouts are? Oh, they are. Fantastic. Okay, thank you. All right. And there's also a small thermoelectric module that is going around the room in a small Ziploc bag. All right. So again, a key thing to point out over here is that both, all three, in fact, the Seebeck, Peltier, and Thomson effects are reversible, meaning you reverse the current flow direction, you get heating instead of cooling, and so on, right? One thing that is not reversible, but often gets mentioned in the same sentence with these, is Joule heating, right? Joule heating basically just means that you're passing a current through a resistor, and the resistor heats up, and that's that, right? You cannot actually take that heat from the resistor heating up, kind of put it back in and get current out, right? That just doesn't work. Thermodynamics doesn't work like that, right? So, and I'll come back to Joule heating because it turns out that Joule heating is actually I guess I would call it a parasitic effect of modern thermoelectric modules, right? Of commercial and practical thermoelectric modules. Okay. Again, I mentioned Seebeck coefficient of about 300 microvolts per Kelvin a little bit earlier. What are some of the typical Seebeck coefficients of typical materials? I didn't search too hard for this from Wikipedia, but here's some numbers, right? So Thomas Seebeck's original junction was copper and bismuth. So copper has a Seebeck coefficient of 6 microvolts per Kelvin. So it's actually very, very small. In fact, I would call it almost zero compared to other numbers. He was lucky, though, because bismuth actually has a reasonably large non-zero Seebeck coefficient. So he was actually able to measure something. But if he had silicon, relatively pure and then relatively purified and then doped silicon and germanium, or selenium or tellurium, these are basically semiconductors, he would have measured a much, much more, impressive result from the beginning. Of course, in the 1820s, he did not have these in very purified form. He just had copper and bismuth and a bunch of the other metals at the time, which basically explains why the original discoveries in thermoelectrics in the 19th century were essentially all done with metals. Semiconductors, of course, really only came to the fore. They were really purified enough and so on at the beginning of the 20th century. So, again, and we'll get more detail onto this, but again, to summarize, metals tend to have low Seebeck coefficient. It's non-zero, but most of them is quite low in absolute value. Semiconductors tend to have, relatively high Seebeck coefficient, but the Seebeck coefficient depends on doping and temperature, of course. Actually, all of them depend on temperature. One thing I forgot to mention on this slide, and maybe I'll write it on the slide, is the Seebeck coefficient of P-type materials, for semiconductors, of course, right, is greater than 0, and the Seebeck coefficient of N-type materials is less than 0, right? So that basically depends on doping. But in absolute value, right, these are all absolute value. These are absolute value, right? So again, it'll depend on doping, of course. It'll depend on temperature. It depends on a number of other things. And I wanted to mention the sign, right? So for P-type materials, it's positive. For N-type materials, it's negative. They're pretty large in absolute value. Okay, so let's talk about the microscopic origins, right? We talked about the discovery. We talked about, sort of how these things look. What are some numbers, maybe? And what are the microscopic origins, right? So materials have electrons. Materials also have holes, right? Those of you who are familiar with semiconductors, of course, are also familiar with the concept of holes, but holes also exist in metals. So basically, holes are just the missing electron. So if somehow you're able to remove an electron from a material, what you're left with is essentially a broken bond, right? So this broken bond actually travels around as if it were a particle with positive charge, right? Even though it wouldn't exist outside of the semiconductor or outside of the material, inside the material, it's essentially literally behaving as a particle with a positive charge. So for the rest of the presentation, I will be treating electrons and holes pretty much interchangeably. One, of course, having negative charge, and the other one, of course, having positive charge. So this is negative, and this is positive. Positive 1.6 times 10 to the power minus 19 coulombs, if we're insisting on units. Sorry about that. I'm trying to write 19, and I'm not really succeeding. This is... there we go. That sort of says 19. All right. So So we have electrons, we have holes in this material, right? And now we have a temperature gradient. So the way I drew it over here, I have a hot end and I have a cold end, right? And look, I've deliberately done this, of course. I've connected an N-type material in series, electrically in series with a P-type material. But they are thermally in parallel, meaning they show up, thermally, well, in parallel between the hot and the cold end, right? So what is happening is that both types of carriers, both the electrons and the holes, will actually diffuse from the hot end to the cold end. Again, this is not something we're unfamiliar with, actually. If you think about, for example, I don't know if in this room this is the case, but many places, if you have a space heater right inside the room, the space heater will heat up the air around it, right? But then, let's say there's a space heater next to that window, but by standing over here about 15 feet away from that space heater, eventually I would feel the heat because the kinetic energy of those hot molecules will actually, just precipitate their movement, their diffusion towards me, right? So that's essentially the same thing that's happening over here, essentially. The electrons and the holes will simply become more energetic due to simple thermal agitation, Brownian motion, if you will, near the hot end, and they will both diffuse, they will physically diffuse towards the cold end, right? However, notice that if the electrons are diffusing this way, that means that the electrons will set up a potential difference like this, V, which is plus over here and minus over here. And of course, if the holes are diffusing, no, actually that's fine. And if the holes are diffusing, it's going to be minus over here and plus over here, right? So essentially what this is going to actually cause is it's going to cause a current flow, right, like this. Okay. Right. So essentially this is what I meant by these things being thermally in parallel and electrically in series, right? Even though they seem to be actually moving in opposite direction, right? They're moving with a temperature gradient. The way these things are actually hooked up, they will actually complete the circuit and the current will actually move basically the way I've drawn the red arrow over there, right? All right. What about the Peltier effect? Well, the Peltier effect is basically just the opposite of this thing, right? So in the Peltier effect, I'm actually driving a current through this whole thing. And as I'm driving a current through this whole thing, the current will actually move the electrons and the holes in the same way I've drawn over here. So it's going to move them exactly the same way. The electrons and the holes will move with the current flow, but the same electrons and holes, they carry kinetic energy. If they carry kinetic energy, which by the way is written over here, if they carry kinetic energy, well, they carry energy, right? So basically this explains why, right, I'm going to be able to essentially heat one end and cool the other end. And also explains, as we'll see a little bit later, why for thermoelectric applications we tend to prefer materials that have higher electroconductivity, which tend to be metals or highly doped semiconductors. It turns out metals are actually not great for the best thermoelectrics, so actually really we're left with highly doped semiconductors. But this sort of simple explanation kind of hints at that. Okay, so I promised a little bit of math for this morning, but not too much math. I don't want to anybody to fall asleep at this slide, and I don't want to go through all the details on here. But basically, the way that people keep track of electron and hole particle motion inside a semiconductor is to start with something called the Boltzmann transport equation. The Boltzmann transport equation, if you listen to really serious button-down scientists, is a 7-dimensional phase-space representation of electron and hole particle motion. 7 dimensions, and I always have to remind myself, what are the 7 dimensions? There are 3 dimensions in space, so x, y, and z, right? And then there's 3 dimensions in momentum, kx, ky, and kz. Right, so we're talking about 3-dimensional momentum and space, right? And then there's 1 dimension in time, right? So that's a 7-dimensional space. It sounds sort of really mind-blowing and complicated, and it is. It actually cannot be solved by a computer, right? So we can write it down, but then we can't solve the equation. So essentially, what we actually do is we play with different simplifications of this equation. The particular simplification that I've used over here is something called the relaxation time approximation. This is the RTA, right? Where I basically assume that the distribution of particles is only slightly disturbed from equilibrium. F right here is the distribution of particles. What do I mean by distribution? It's basically the probability of finding a particle somewhere in space, right? The equilibrium distribution of particles for electrons and holes is written over here. This is actually something that was worked out by Enrico Fermi and Paul Dirac. This is called the Fermi-Dirac distribution. Fermi-Dirac distribution. Okay? And this is the equilibrium distribution, of course. And what this term right here says, this is the equilibrium distribution, and this is the departure from equilibrium. So basically what this term essentially says is it says, well, you know, I've got the electric field force acting on the material. I've got the velocity. I've got the spatial gradient. This is gradient in space right there, gradient in momentum. Notice that space and momentum are actually treated kind of mathematically symmetrically in a way, if you will, right? But the sort of more important part that I'm talking about over here in the relaxation time approximation is the right-hand side of the equation, which basically says, look, I'm going to make a simple assumption that the system is not disturbed from equilibrium too much. So there's a certain equilibrium distribution. This electric field that I applied is only shifting the distribution a little bit, right? And then there's a scattering mechanism that's actually bringing the distribution back into, you know, equilibrium, I suppose, right? This is like basically saying, you have a car at rest, right? So it's sitting in the parking lot, but then you're driving the car very slowly. And we're driving the car very slowly, right? You can actually almost exactly calculate you can almost exactly calculate the force of friction with the air around your car as you're driving. So this is basically the equivalent of that force of friction, right? They're restoring sort of the equilibrium to the distribution. Okay, so you know enough about that. If you actually know what the distribution function is, and if you know what the scattering times are, and if you know what the temperature is, of course, Kb, and there's the Boltzmann constant, right? So basically things that in general we should know. You can actually calculate the electrical conductivity and the Seebeck coefficient using these integrals over here. So the electrical conductivity is basically just this integral over what is known as the differential conductivity, and it's written down here. Differential conductivity, of course, depends on charge, as it should. Depends on the scattering times. The longer scattering times there are, the longer. So the longer you have between scattering events, right? Of course, the conductivity is higher. The larger the velocity of your particles, of course, the conductivity is going to be higher. That makes sense as well, right? And then there's sort of a fourth mysterious term over here called the density of states. And I'll talk a little bit more about the density of states in a moment. Over here, this is just the derivative of the distribution function, which will actually make a lot more sense on the next slide, but you can actually thumb through that and look ahead and see what this derivative here looks like. Then the Seebeck coefficient actually looks very, very similar to that, except it's kind of weighed. So if you kind of squint and you see this, you'll see that it's weighed, so you can kind of recognize these terms. So you have the energy term right there, which is of course what's actually this is carrying. And then maybe I'll switch colors. And the term around it is actually this differential conductivity that I saw above, right? So that's basically what it is. So it's kind of using the differential conductivity, right, the speed of the particle, so to speak, to weigh how much energy the particles are carrying. That's probably, you know, one way to look at it, right? And so, again, this is measuring how well the conductor is carrying charge, right? That's conductivity, what it means. And this is basically measuring how well the conductor is carrying energy, thermal energy specifically, but energy nevertheless, in, you know, the midst or with an electric field applied. Okay, so now let's talk about the density of states a little bit. The density of states, abbreviated DOS over here. The density of states is one of these concepts that you know we learn in quantum physics classes usually, but it actually turns out to be incredibly useful for describing anything that happens in solids, including the little Peltier generator which I passed around the room. The density of states basically tells us how many states there are available in a metal, or I'm sorry, in a material. Right? Okay, what does that mean? Well, again, if you think about electrons as cars, which is actually turns out to be a very, very helpful analogy. If you think about electrons or holes as cars, and then you should think about states as parking spots, right? So, for example, I don't know where the parking spot is because the blinds are down, right? But for example, you know, you can have a parking lot that has lots and lots of states, lots and lots of empty parking spots, right? But only 2 or 3 cars in it, right? Or you could have a parking lot that is completely filled, right? So you have 1 electron or 1 car in each state. That's basically what this is, right? And again, the reason electrons are very, very analogous to cars in a strange way in this analogy is because you can really only put 1 electron per state. This is also known as the Pauli exclusion principle, right? And this is something that people kind of figured out really 100 years after you know, thermoelectrics was discovered, actually. Thermoelectrics were discovered sort of empirically, right? But people kind of figured out the math. It took them 100 years to figure out the math. And the math is really, sort of relies on pretty complex quantum mechanics that was developed in the 1920s, maybe 1920s and 30s, right? Okay. So, we're not going to get into the exact calculation of the density of states. There's very, very good references, some of which I actually provided in your handouts at the end of the slides. But these things can be done. They actually can be done with pencil and paper. And one thing that I want to point out is that in metals, it turns out, the density of states simply is relatively constant. It just does not vary very strongly with sort of the average energy. I shouldn't really say the average energy, but the average sort of transmission energy of the particles, right? So you can actually see here density of states is a function of energy. It's really a slowly varying function right where these particles are being transmitted at, right? On the other hand, in semiconductors, it turns out, I can actually arrange the doping of the semiconductor in such a way that I can transmit most of my carriers somewhere where one of these density of states actually ends, right? So in a strange way, this is sort of where the analogy doesn't really work as well with cars. But you could sort of think of it as, this is where the parking lot ends. And for some reason, it is actually better to move cars right where the parking lot ends. Maybe that's where the actual, there's a little path over there. So if you want to move a car from one spot to another, you can't just go, cutting across the parking spots. You actually kind of have to go, around all the cars and really at the edge of the parking lot. And that's basically essentially what this is telling me over here, right? Another thing that maybe I should mention is that, in general, we want both high density of states, we want, high density of states for some applications, but low densities for other applications. In metals, my density of states is actually too high, right, at the point where I'm transmitting all the carriers, which actually means that I have high effective mass of the particles, which basically means that I actually have low electrical conductivity. Actually what I want is not only do I want, relatively, decent density of states, is I also want a huge discontinuity in the density of states. So maybe I'll switch back to red over here. So really what I want is discontinuity in density of states, right? And that's basically, this is what I said here, what I called here, density of states vary sharply. That's the same thing as having a discontinuity, right? So this is this concept of parking lot, sort of failing me a little bit. But I guess, like I said before, maybe the only way to think about it is maybe to say that, look, the parking lot is sort of ending over here. It's ending sharply, but there's actually an access road on the edge of the parking lot, right? So it's much, much easier to actually move energy, cars in this case, if you're going by the edge of the parking lot than if you're actually trying to move, particles right in the middle of the parking lot. But that's maybe not a very fair analogy to electrons or to cars. Okay. So, having sort of seen that, and that's probably the most sort of, mathematically intensive, set of slides that I've shown, is, we should maybe talk about the efficiency of these thermoelectrics, right? So, how efficient really are thermoelectrics? That's a very good question. It's a very practical question, right? It turns out, again, if you take a look at a thermoelectric device, such as the one that I'm passing around the room, what you end up with is you end up with all these legs, N and P in series, electrically in series, and thermally in parallel, right? However, if you're actually flowing current through all of these things, what you actually end up having is you end up having a little bit of parasitic Joule heating inside of each one of these legs, right? Of course, you end up having the Peltier effect in this case happening at these interfaces, which is the good thing. That's the actual heating or cooling. But you have this parasitic Joule heating happening in there. And not only that, but you'll actually also have heat conduction, what I call backflow heat loss between the hot end and the cold end, right? So I think sometime, in the 1920s, 1930s, people recognized this for the first time. And they realized, if we actually need to optimize this thing, if I really want to optimize the highest cooling or heating efficiency of a thermoelectric, really I should be optimizing the sum of these things. So this is the Peltier effect in there, which gets a plus sign, minus the Joule heating loss, minus the heat flowing back from the hot side to the cold side, which is not something that I want in this particular Peltier cooling application, right? And it turns out, again, if you actually work through the math, it turns out that this will be maximized, the heating or cooling power will be maximized when I maximize something called the figure of merit. The figure of merit is also known as ZT. Z is technically the figure of merit, but T is temperature. But people usually talk about these two together, probably more for convenience than anything else, because Z has units of 1 over Kelvin, so ZT will have basically no units. So it's a sort of a very nice round number, right? So it turns out what goes into this are fairly fundamental material, parameters. Seebeck coefficient squared, check. We kind of know what that is. The electrical conductivity linear, we also very, very well know what that is. Of course, we know temperature in there. And it turns out the whole thing is inversely proportional to the thermal conductivity of these little legs. And that kind of makes sense, right? You would expect a thermoelectric module to be more efficient if if its Seebeck coefficient is higher. In fact, you get, sort of twice the bonus, not twice the bonus, but square the bonus, right? If Seebeck coefficient being higher. You would expect it, as I said earlier, if it has a good electrical conductivity, to also carry heat a little bit better. I expect maybe temperature to play a role because, as you can expect, if the average temperature of the module is higher, the Brownian motion of electrons and holes inside the module will be higher, so they will actually also diffuse better, right? And I expect that the thermal conductivity is probably going to need to be low, because if the thermal conductivity is high of these little legs, I'm actually going to have significant heat flow, backflow loss, as I mentioned over here. So the heat will actually sort of flow back from where you're trying to put it to where it's trying to get away from. It'll just kind of come back, right? And that's basically a parasitic loss, right? Okay, so that kind of makes sense, to me. I think those are the things that we really need to optimize. Okay, one thing that I do want to point out, and I pointed out already here in sort of grayish fonts, is that the thermal conductivity of a material is not just the thermal conductivity contribution of electrons and holes, because of course they carry energy, so of course they carry heat, we already know that. But it's also the lattice contribution of thermal conductivity. And what I mean lattice is I literally mean the atomic vibrations, right? Some people call those phonons, right? The sort of more technical term is phonons for this. So this is also sometimes called kph, phonons, right? This is KL. But I like using KL because I get to use one single subscript, and it's more convenient than using kph. Less typing to do, right? Okay. So, again, just kind of let's look at this a little bit more depth, because this is a very, very important concept, and this is really how we optimize these things. So again, there's the equation again. There's the two components, Ke and Kl, the electronic, and then the lattice thermal conduction. And so what we need to do to get really good thermoelectric devices is to simultaneously maximize S, sigma, and minimize K. Turns out this is very hard. This is basically where all the thermoelectrics research, or I shouldn't say all, but most of the thermoelectrics research over the last, 50 years, right, has been, maybe even more than 50 years, right, is we've been actually trying to simultaneously maximize S and sigma and minimize the thermal conductivity, right? You could say, okay, fine, you should also maximize the temperature, right? But that depends on the application, right? So if I need to do some energy harvesting at room temperature, I'm kind of stuck with T at room temperature. If I need to do some energy harvesting, inside a car engine, well, I'm kind of stuck with 600 Celsius or whatever the local temperature is, right? So T, I don't think necessarily, depends on the application, right? Okay. So this I kind of already mentioned. I said these things are interrelated, and I said that the thermal conductivity is really the sum of the electron and the lattice or phonon contributions, right? And so, one thing actually that turns out is that it turns out that increasing the electrical conductivity also leads to an increase in the electronic contribution to thermal conductivity. That is basically what is happening over there. So, there's almost, so to speak, there's no free lunch in thermoelectrics. Okay, so let's look at this a little bit, pictorially from some folks who maybe, let's say, have already thought about optimizing this, right? So what we're plotting over here is I'm plotting basically all the quantities that I mentioned earlier, the Seebeck coefficient, the electrical conductivity, and then what's called the power factor, S squared sigma. You notice that shows up in the denominator, in the numerator of the fraction I showed you earlier. And here at the bottom, I'm showing the thermal conductivity with its two contributions. One is the lattice contribution, which is basically constant, at least with respect to what the independent variable here is. And the electronic contribution, which of course increases with the independent variable. And the independent variable in this particular example is the free carrier concentration. How do I modulate the free carrier concentration in most materials? I dope them, right? In metals, this is very hard to do, by the way, because metals have humongous carrier concentrations. Though, of course, in semiconductors, this is basically shown for a semiconductor, And these are units of sort of reasonably high doping densities for semiconductors, 10 to the power 25 per cubic meter, right? Something like that. Okay, so what's actually very, very interesting, again, without necessarily getting into all the derivations, but the derivations do come out of the Boltzmann transport equation formalism that I showed you earlier, is that as I actually start doping a semiconductor or material in general higher and higher, of course the electrical conductivity goes up. So sigma goes up, 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 because I'm increasing the conductivity of the material. I'm increasing the number of carriers available for transport. Unfortunately, the Seebeck coefficient actually comes down because I'm making the material more metallic, right? So remember, metals don't have very good Seebeck coefficients, whereas semiconductors, certainly purer semiconductors, have very good Seebeck coefficients. And so essentially what's happening is really the power factor, which is S squared sigma, will have some sort of an optimized maximum somewhere in between, somewhere where S has already decreased a bunch and sigma has already increased a bunch, right? You can actually see that over there, right? So there's clearly an optimum doping concentration that will maximize the thermoelectric figure of merit for a given semiconductor, right? The other thing I want to point to is that the thermal conductivity, again, I mentioned before, it has essentially a lattice contribution, which is constant. It's not really a function, it's not really a strong function, I should say, of the carrier density, right? But the electronic contribution is a strong function of carrier density, as it should be. It's basically linear in the carrier density, right? And it turns out the electronic contribution is basically directly proportional to the electrical conductivity, right? So this sigma over here is the same sigma that is shown over here, right? This is that sigma right there, right? So, and the proportionality constant is basically what's something called a Lorentz constant listed over here, and the temperature, which is whatever the temperature of your application is again, right? So there's not much we can do about the electronic contribution. Unfortunately, I have to increase the electrical conductivity up to a point, so I'm going to have to live with the fact that this is essentially increasing. Unless I'm actually trying to, do things at a different temperature, or unless I really try to muck with this reasonably, almost universal constant known as the Lorentz constant. That's very, very hard to do. So instead, what do? Instead, what we do in practice is we really try to focus on minimizing the lattice contribution of the thermal conductivity. So here are the two key knobs for optimizing thermoelectrics. One of them is we basically play with the carrier concentration to maximize the power factor. You can actually see how that's done over here. And the other thing that we do is we minimize the lattice thermal conductivity. That's it. These are the two sort of most obvious knobs, or easiest to also handle knobs for manipulating, for optimizing the thermoelectric properties of material, right? Okay. By the way, I like thinking about sort of hypothetical situations where I've really optimized something as much as I can optimize, right? And one such example is, what if I've minimized the lattice contribution of thermal conductivity to the point where the lattice contributes 0 to thermal transport, 0. It's not possible in practice. Even, plastics or glasses, which are very poor thermal conductors, actually have a non-zero thermal conductivity. But let's say that we've reduced it to 0. It turns out if hypothetically I reduce the lattice contribution of thermal conductivity exactly to 0, again, not possible, but let's say I did it, then I can actually estimate the maximum ZT of my material, right? This maximum ZT of my material is basically very simple to calculate, just using the previous expressions and this expression over here. It just ends up being S squared over L0. That's it. The temperature cancels out. You're just left with the Seebeck coefficient squared divided by L0. And so it turns out the Seebeck coefficient, the maximum ZT is about 3.7, it turns out, if you use a reasonably high Seebeck coefficient of 0.3 millivolts per Kelvin. This is really the maximum ZT, maximum thermoelectric figure of merit that you can obtain from a material. So now I know that for a real material, I'm not going to be able to do better than that. This is really the maximum, right? So this is kind of a valuable thing, because if you ever read, a new press release about some work done at some, university or lab, and they claim, a really, really large, thermoelectric figure of merit, the first thing I would look for is I would start to look forward to seeing if it's actually exceeding this sort of fundamental limit, right? If it's exceeding more than that, then something's wrong, right? I don't think most people would really make that mistake, but there's certainly a lot of sort of confusing data in the literature at the moment, right? There's also confusing claims. Okay. Before we get into the confusing claims, let's maybe talk about, again, commercial materials. The commercial materials have had ZT close to 1 really between 0.6 and 1 for, a really long, for a very wide temperature range between about 300 Kelvin and about 1200 Kelvin, right? And for the last, 50 or 60 years. I have a plot on that in a few moments, right? I do want to point out that choosing your material for thermoelectrics really depends on your application temperature. So if you want to do things at room temperature, you probably better use things like bismuth tellurium or lead tellurium, right? So something based on lead, bismuth, or tellurium. These are sort of the materials, of choice. There's the periodic table. These are the materials shown over there, right? If, on the other hand, you want to do something at really high temperatures, right? And we'll talk about some high temperature applications. Silicon germanium is actually not a bad choice. It's a lousy choice at room temperature, but it's actually a pretty good thermoelectric material at temperatures above 1000 degrees Kelvin. So, it's also cheaper. Silicon germanium will tend to be cheaper than bismuth tellurium, right? So again, the bottom line is not all materials are good at all temperatures, and you really need to kind of choose your material optimized for the temperature range at which you actually want to operate. Okay. I had actually kind of mentioned that we've been sort of stagnating in this field for about 50 years. It turns out that in the 1950s, bismuth tellurium was discovered, and then we've sort of been stuck at a ZT of about 1. Right? So we've been stuck at a ZT of about 1, and only around the year 2000, people started, nanostructuring materials and coming up with thermoelectric materials that don't exist in nature, okay, which actually have a better figure of merit. And this is where things get a little bit dicey. Somebody claims a ZT of 3 and somebody says, no, you did the measurement wrong, right? And there's sort of all these sort of heated debates in the literature. And so most of the thermoelectrics that you can buy today are still kind of, certainly the more inexpensive ones, are still basically based on bismuth tellurium and similar types of alloys, right? But there are, discoveries in various labs, things that haven't yet quite been scaled to practice, usually using some sort of nanoscale features, right, to actually obtain a larger than 1 ZT, right? These are sort of very, very interesting, very, very round numbers, right? I should also mention that I'll talk a little bit about quantum effects in thermoelectrics in just a moment, but I should basically mention that pretty much it's been decided that most of the improvements that have come as of late in thermoelectrics have really come from artificially lowering the thermal conductivity. So essentially what we do is we put in multiple interfaces, multiple barriers, and things just get scattered. Electrons get scattered, the atoms get scattered, right? And so heat just does not flow very well across these nanomaterials, essentially, right? So you're able to actually block more of the heat, and somehow if you can block more of the heat but somehow still conduct enough electricity, then you can actually maximize your ZT. But that's really where most of these improvements actually come from. They actually come from the thermal, not the electrical engineering part of these materials. How do we lower thermal conductivity, right? This is sort of it's a cool picture I found in a paper by Ali Shakuri, who's now at Purdue University, and whose paper I'm listing among the references. Again, these are electrons. You can see the electrons in red. You can actually see, these are the lattice vibrations. These are vibrations, right? So we have to kind of represent them as a little wave, right? And so what we need to do is we basically have to introduce features inside the lattice that scatter the atoms, the actual phonon vibrations of the atoms, but do not actually scatter the electrons. And this is very, very hard to do in practice, because if you introduce, defects randomly, or if you introduce vacancies, or if you introduce, even dopants randomly, it's typically going to scatter both electrons and phonons, right? So really kind of the catchphrase that was come up with, Slack came up with it in the 1960s. The catchphrase is basically what we want is we want a phonon glass and an electron crystal, right? So really we want a material that behaves as an amorphous glass as far as the heat flow for phonons is concerned, but we actually want something that behaves as a beautiful crystal as far as the electronic features are possible, right? From a point of view of material science, this is not something that's really, possible, right? But you can get things that kind of look like that. And we can actually do that by taking advantage of the fact that the wavelengths of electrons and of phonons are actually not exactly equal. So you can actually split things up that way. Okay. Again, a little bit more on how do you actually reduce the lattice contribution to thermal conductivity is you use nanoscale scattering features. The lattice contribution of thermal conductivity is going to be proportional to the mean free path, between collisions, right, for the phonons. So one sort of reasonably simple way to do this is to design what are called superlattices. I don't know if I wrote the word superlattice in here, but these are superlattices. They're not just lattices, they're better. They're called superlattices. Right, SL. Or to use some sort of a polycrystalline material. Right, so that's this superlattices. And you can see here, you can see the periodic arrangement of these layers, right? So that basically means that phonons will be reflected, right, from the different interfaces. They will actually turn around. And so the thermal conductivity of these multi-layered, these are alternating silicon and silicon germanium SL. See, the word right there says SL, that's a superlattice, right? It turns out the thermal conductivity of these superlattices is actually significantly lower than the thermal conductivity of the constituent elements, which in this case are silicon and germanium, right? I think now a reasonable question might be, well, gee, you introduced all these interfaces, but how come they don't scatter electrons? How come electrons are actually able to somehow, go through the multiple interfaces? Yes, of course.
So what is the thickness of the alternating silicon and germanium, and what's the deposition technique for that?
Yeah, that's a fantastic. Yeah, it's actually a very good question, and I apologize for normally I would have a scale bar on this thing, but I somehow lost my scale bar.
I have the top image, and it doesn't have a scale bar on it, so I didn't know.
Right. So the let's see if the scale bars are actually listed over here. The periods are actually listed over here. 300 angstroms, 150, 75, 45, right there. So those are those numbers, right? So they're on the order of angstroms, right? And obviously the one that will, not obviously perhaps, but the one that actually has a smaller period is going to have more scattering, obviously, because you have more interfaces. However, if you actually change the stoichiometry of your material, you can actually do with an even larger period as well, right? So that's this particular picture. The period is 15 nanometers or 150 angstroms, right? And these are usually, I want to say these are deposited by molecular beam epitaxy, but I'm actually not sure, right? I know if these were 3.5s, they would be molecular beam epitaxy. For silicon and germanium, I simply do not know, but if you send me an email, I can actually send you the paper where I pull these from. These may also be available in the documents which are at the end, which I listed at the end of the slides, where the references are.
That would probably make sense because metal organic CVD couldn't have it epitaxy.
That's right. That's possible. It's possible. But I'm simply not sure in this particular case. And so basically what's happening over here is that, the electrons, depending on the period, which is basically listed over here, depending on the period of these things, the electrons may actually be able to tunnel through the multiple interfaces, whereas the phonons will actually scatter and come back, right? And that's why the period of these interfaces is actually very, very, tricky, not very tricky, but very important to play with. But it's not just the period, it's also the stoichiometry of the materials. And of course the stoichiometry matters because, these materials have different masses, right? Silicon is lighter than germanium as an atom. So playing with the masses of the atoms, as you can imagine, is also going to affect the vibrational modes of these particular superlattices, right? So that's kind of another thing happening over there. Another method for doing this is also to introduce polycrystalline materials, right? Polycrystalline materials also tend to introduce lots of interfaces. And again, if you play with the size of the grains inside the polycrystalline materials just enough, you could actually, again, create, the grains to be small enough for the electrons not to really see them, but large enough for the phonons to essentially get really scattered. Okay. Other way to reduce thermal conductivity without necessarily significantly affecting electroconductivity is to actually use edge roughness. So this was actually a work that was done at UC Berkeley back about 6 years ago now, and basically what they did is they actually measured the thermal conductivity and the Seebeck coefficient of rough silicon nanowires, right? And at the time they kind of went on a hunch, right? And they said, hey, we're going to do these measurements. We just kind of went on a hunch, right? But there wasn't a particularly good mathematical understanding of why this is actually happening. The result was there. It was very big news at the time. And when I was back at the University of Illinois in Urbana-Champaign, we actually came up with a relatively straightforward theory for understanding why phonon scattering from these rough interfaces actually affects the thermal conductivity as strongly as it does, and it does not affect the electrical conductivity nearly as strongly as one would have thought. So this is basically another knob. Basically, playing with any kind of spatial features, be it superlattice spacing, polycrystalline grain size, or edge roughness, features, can also be used to change the thermoelectric properties. In 1993, there was a very interesting paper that came out of MIT, so about 21 years ago, right? There was a very interesting paper coming out of MIT which suggested, theoretically, in theory, if we stopped using three-dimensional materials and we started using one- or two-dimensional materials as thermoelectrics, we would actually get quantum confinement effects, which would lead to these sharp changes, these sharp asymmetries in the density of states of our materials. And again, these scientists showed with pencil and paper, effectively at the time, that basically you should actually get a significant increase in the Seebeck coefficient if you have these sort of sharp increases. I'm not going to get into necessarily the math, but again, I just want to invoke for a moment this concept of density of states, which is basically this concept of the parking lot, and suffice it to say that the density of states looks very different in 1D and 2D compared to 3D type materials. Right? I should mention that in practice, this works a lot better on paper than in practice. In practice, when you have a relatively large system, if you want to carry a certain amount of heat, you still need a relatively large system. And in practice, it turns out that a lot of these quantum features actually become blurred if they're even slightly non-uniform. So, but let's say you put a bunch of nanoparticles inside your material, but if the nanoparticle size varies just a little bit, these edges of these energy levels are actually going to be quite blurred. So you're going to lose some of the advantages. It turns out in practice, most of the breakthroughs that we think have happened in the last 10 or 20 years have really actually occurred from a reduction in the lattice thermal conductivity rather than an enhancement of, or sort of proportionally more has happened from a reduction in thermal conductivity than from enhancement in electrical conductivity or electrical properties of these materials. Of course, it doesn't mean that this cannot be done. The physics is very sound. It should be doable. It might be just a manufacturing issue. How high of a ZT do we need? Remember, ZT today is about 1, maybe a little bit higher than 1 for some, certain combinations of materials. How does the actual efficiency look like when compared to other, engines, I suppose, right? Other methods for generating work, right? Well, if you think about modern mechanical refrigerators, such as the one that we have at home, the cooling efficiency of those refrigerators, right, is equivalent to a thermoelectric with ZT of 3. So that's very high, actually. That's not really something that we really have commercially available today for thermoelectrics. That's why thermoelectrics are usually, working in niche applications where having, mechanically moving, refrigerator is not necessarily a good thing. And also, if you're thinking about electrical power generation, steam power plants, right, which operate, well, on steam, on water vapor, hot water vapor, right, they're basically 40% efficient. 60%, of course, is lost as heat, which we can still harvest using these thermoelectric generators. But still, if we're actually just talking about making electricity using heat alone from a campfire or, burning fossil fuels, I suppose, right? We just don't have that kind of efficiency. In fact, you can see over here, using the, maybe I should circle this, using modern thermoelectric materials at sort of, reasonable ZTs and so on. I'll switch to red. Is down here somewhere. The efficiency is about 10%. It's not 40%, right? So even the best thermoelectric power generators today really only have about 10% efficiency, whereas steam power plants are converting about 40% efficiency of the overall energy that's actually going into the steam, right? So, we kind of have to keep these things in mind. All right. There are a few alternatives, and, I think yes, I'm sorry. Of course. Yes.
Please relate ZT around 3 to 40% efficient for me.
Yeah, so that actually...
These are two different measures.
These are two different...
I'm not sure how they're related.
That's right, no. So these two, well, you can relate the ZT and the efficiency through this equation right here. That's basically where that comes from, right? And the ZT is in there, the rest are just constants. This is the cold end of the heat engine, and that's the hot end of the heat engine. So that's basically it, right? These two are actually, this is roughly correct. So ZT of about 4, and this is ZT of about 2. So ZT of 3 would be somewhere in between, right? And if you go to really high temperature, right, you would see that sort of asymptoting to about 40%. But these two are actually not taken at the same ZT. These were, like you noted, these are actually a little bit different metrics. This is for refrigeration, and this is actually for power generation, right? So this is the Peltier effect, and that's the Seebeck effect. But I'm comparing them with sort of the commercially, relevant technologies that are in use today, right? Big fridges we have at home, and then the steam power plants for making electricity. All right, but that's where the equation for efficiency comes from. I think in the interest of time, I'm going to skip the next two slides. The next two slides are actually talking about alternatives to thermoelectrics. This is actually something called thermionic energy conversion. And it basically employs a concept known as energy filtering, hot electron filtering inside a semiconductor. I don't want to talk about this because, like I said, I'm running a little bit short on time and I want to get to applications. But you can read more about it in a reference by Shakuri from 2010 among the links I provided at the end of the document. Another alternative is something called thermophotovoltaics, which again, is not thermoelectrics, obviously. The thermoelectric concept is illustrated there. The thermophotovoltaic concept is illustrated over here. And here we're basically just using a black body heat source, and we're converting the heat source essentially to electricity using a regular PN diode, okay? So there are some pluses and some minuses, of course, to using either thermionic, thermoelectric, as well as thermophotovoltaic converters. Some of them are listed over here. Of course, these are research topics today. I just kind of wanted to have them for completeness, but this talk is obviously not Thermophotovoltaics 101, it is Thermoelectrics 101. So I just wanted to put them in very briefly. Okay, so this ends the sort of the more fundamental side of the talk, and I will be happy to stop for a second, have a sip of my coffee, and take any questions. Yes?
How do you relate ZT to, I mean, I think that is like open circuit voltage to the actual amount of
power. Yeah. Yeah, I actually have that in a few slides. So if I may answer that question in a few slides, I'll get there. Yeah, there's a connection actually between them. The short answer is it really depends on the external load of the circuit, so to speak, that you're connecting this to, right? So it depends on both on the internal load and the external load, because the actual thermoelectric generator has an internal resistance itself, which is a parasitic, obviously, right? But there's actually an optimum that you can use. So you really have to match your thermoelectric generator with the load that you're driving. There's another question here.
Is there any correlation or intersection between thermoelectric materials and superconductivity?
So superconductivity, as you know, is a phenomenon that's happening at very low temperatures, right? I don't know what the world record for high temperature superconductivity is, but certainly the superconductivity I learned as an undergraduate in physics was, occurring at 4 Kelvin or something like that, right? Here we're talking about, very high temperature phenomena at room temperature and above, right? Where we have heat engines and we're trying to harvest, large temperature gradients, right? So it would appear that those two are kind of, just two separate parts of the materials world, right? But it turns out that, some of the materials that have, decent thermoelectric properties, or properties relevant for thermoelectrics, also, if you take them to low enough temperatures, they also have properties relevant for superconductivity, right? So there are some overlap in materials, and also there are, I guess another connection might be, some people do care about cooling electronics in outer space. So you really want to cool something electronic from, 10 Kelvin to 2 Kelvin using thermoelectrics, for some reason, right? So, but that maybe there's really no connection there, except maybe just the same temperature range.
So so some of these materials might support two repairs at a low temperature?
They might.
But that's coincidental.
As far as I know, yes. I mean, I don't think, first of all, so I think the communities that usually think about these two are very diverse, different types of communities. So I don't know how much crosstalk there is between the two communities. I'm certainly more of the thermoelectric community than the superconductivity community. I simply, don't think that people have really thought about sort of optimizing the two. And I'm sort of struggling to come up with a reason for that. There might be a reason, but I just cannot think of one. Yeah. Yes?
You talked about the evolution of the figure of merit.
Yes.
Time.
Yeah.
I'm just looking at the charts, going back to the previous question. Are modern thermoelectrics around 1?
They're around 1, yeah.
So they're not, none of them are really reaching 3.
No, not the ones we can buy commercially, as far as I know. That's right, yeah. The one that I passed around the room, I bet it's bismuth tellurium ZT of around 1. I have the data sheet in my office, I forgot to bring it, but it'll tell me what it is. The one, I was actually going to pass this around. This is a really fun thermoelectric thing, and if you have a laptop or with a USB port, you can actually play with this. So now that I'm switching to applications, I was going to, well, you saw a module already, but this is actually a real working thing. So if you have a drink that you'd like to cool or heat using your USB port, you can do it while I'm talking. It's not very efficient. But you know, I bought this for about $15 from eBay or something, or Amazon a few years ago. But it's kind of fun. It's one of those things I keep on my desk, and so it has a switch right here. I mean, you can see these are actually completely reversible. It doesn't even have an on-off switch. You just plug this into your USB port, okay? But it has a switch right here, and one shows a cup of coffee, and the other one shows a snowflake. And you know what that means, right? Right now it's set on snowflake because, I don't know, it's just more fun to see something cooling by passing the electric current. I think to me, at least, you know, if I switch it to a cup of coffee, this thing will just heat up, right? But that's not that magical to me because, you know, I can pass electricity through any resistor and it'll heat up, right? But the fact that I can actually put this on the snowflake and it'll just run current the opposite way and it will actually cool the surface down is actually kind of cool, right? At room temperature. And people, you know, this is not a very efficient one, but people, you know, you can actually freeze water at room temperature with something like this, right? Or not at room temperature. Starting from room temperature, you can freeze it just in ambient conditions. So I will pass this around. If you don't have a USB port, just, you know, look at it and give it away. But if you have a USB port, you're welcome to try it out and see how slow it is. Part of the reason why it's slow, though, I shouldn't knock it too much. Part of the reason why it's slow, besides the fact that it was cheap, part of the reason it's slow is because my students actually took it apart. And when they took it apart, they removed the thermal grease. This is a very low-tech, you know, feature inside it. There's a thermal grease that connects the thermoelectric module. The thermoelectric module, by the way, inside of that looks just like the one in the Ziploc bag that I passed around. The thermal grease that connects the thermoelectric module to that aluminum surface has been removed by my students because they took it apart a bunch of times and put it back together. So there's a thermal contact in there, which is sort of a very low-tech issue. But we talked about quantum mechanics and all these weird phenomena, and, you know, thermal grease is killing this particular thing. But it sort of illustrates, right, how you know, practical applications oftentimes have very prosaic sort of limitations. You know, thermal grease has been scraped by an undergraduate, and, you know, there it is. Anyway.
Does it make the coffee hot enough to be drinkable?
No. I've actually tested it. Before anybody took it apart, I tested it, and I was able to, so I'm going to say this in Celsius, but I was able, you know, what's room temperature? About 20 Celsius, let's say. I think I was able to cool it down to about 10 Celsius, and I was able to heat it up to about 40 Celsius. Maybe 35 Celsius, so kind of skin temperature, but that's not for this thing. It also works a lot better if you have a metallic can because the metal will conduct heat much better from the little surface. Whereas if you have one of these insulating cans, of course it'll never work because you're just going to insulate. This is just very insulating, right? So you can't cool or heat it.
So not a good wine cooler either.
Not like that, no. But of course you can buy wine coolers based on the exact same technology at Costco for a few.
But they're not USB wine coolers.
They're not USB wine coolers. That is true. Well, right, because you know, that's right. That's right.
Someone drink all these.
That is true. All right. So anyway, you know, I think the application side is I think it'll go a little bit faster because I don't have equations anymore. It's basically just, you know, pictures and sort of talking about trade-offs, right? Including thermal grease as really one of the trade-offs. So this is the module that I passed around. It looks exactly like that. You can see the little legs. You can barely see the little legs in there. If you have not seen the module, who has the module right now? Where did it stop? Oh, no, the little Ziploc bag. Oh, thank you. If you have not seen this, I'll be happy to pass it back if you came a little late. This is basically what's inside the USB thing. You can see the little thermoelectric legs, and you can see the current leads coming in and out of it, right? So there's the wine cooler. There's a fancy car seats. You can actually get cooled car seats in certain high-end automobiles. And of course, power generation. It turns out the Curiosity rover on Mars is operated by Thermoelectrics, which is kind of fun. It's not solar. It's all thermoelectric power generation. And of course, there's these thermoelectric power generators that people are putting on catalytic converters on cars. But before I get to those, maybe I should talk about sort of the most, banal, the most trivial application. They're really thermocouples, right? Meat thermometers. So a thermocouple, again, this is the original Seebeck experiment, right? It's connecting two metals of slightly different Seebeck, coefficients, okay? And so that's where they're soldered, and you stick the soldered part into the temperature, the high temperature where you're trying to measure, and you measure the voltage across the leads at the end. And essentially that's what the meat thermometer is doing, and we have all of these inside our water heaters or boilers and so on at home, right? Typically, you can also do this on your own. You can connect these things to a multimeter, and you can basically measure temperature with a thermocouple on your own, just with a multimeter, obviously. Right? So that's kind of the simplest example. This is recap, so this will go really fast. This is, again, just to remind ourselves that we're dealing with electrons and holes, right? We need to carry heat and cool a body, for example, a cup holder, right? We need to have good electron and hole conductivity. We need to also block backflow through these materials, right? I should mention that, obviously, I mean, this is sort of, again, it's probably pretty obvious, but these things have no moving parts, right? The only moving parts are the electrons, right? And the electrons are very quiet when they move, it turns out. So, and very reliable too, right? We have electronics that operate for decades, right, without any kind of problem. And they're also obviously clean power generators because there are there's basically no freon, no any kind of ozone destroying things in them. This is kind of fun. I found this picture of a lady in the 1950s operating a radio from a gas lamp, right? So there's an oil, actually it's an oil lamp. I'm sorry, I think it's kerosene lamp, right? And she's operating a radio. And basically after the World Wars, there was a lot of interest in thermoelectrics. It's actually kind of fascinating to read about how a lot of the advances were kept top secret in the 1950s and 60s between the US and the former Soviet Union. But in the 50s already people had demonstrated cooling from ambient to 0 Celsius using the newly discovered bismuth tellurium, which is in what I passed around. In the 1950s is when these first radios popped up, both in the US as well as in Soviet Russia, powering radios and doing energy harvesting. Of course, the modern version of this, you can buy at rei.com for $130. You can basically buy a phone charger that doubles as a camp stove, right? So that's exactly right. In fact, this is one of the, I just have to have this. I don't own this, but I discovered it on rei.com looking for something completely different. But it is there. This is very, very fun, right? You put your burnable, you can actually put, they have pictures on, actually a movie online, right, where you can put little like twigs, basically. They want you to put twigs inside this thing, set them on fire, and then charge your iPhone. So it's really kind of fun. All right. So it works in the dark, unlike solar things, right? So, speaking of the dark, by the way, there's fewer things darker than outer space, or certain parts of outer space at least, when you're not really near a star. Radioisotope thermoelectric generators have actually been in use by NASA for 50, 60 years. And this is basically what's powering the Apollo, the Voyager, the Viking, and even the Curiosity mission on Mars right now, right? They're also, I was reading, these are also actually powering, these thermoelectric power generators are also actually powering lighthouses in Russia. So back in the north side of Russia, where it's very, very difficult to get a power grid sent out, they still need lighthouses for ships that skim the shore, and they're basically powered by thermoelectric generators. And the way these things work is that the radioisotope thermoelectric generator basically works by putting a heat source inside, which is plutonium-238. Now, plutonium-238 is not the worst kind of plutonium, it turns out, but it's a very, very good and reliable source of heat. So plutonium-238 will decay into other things like lead, and it has a half-life of 90 years, which means that over 90 years, it'll generate a lot of heat. In fact, I've seen pictures online of this plutonium-238 where it gets so hot under its own decay that it glows, right? So it's basically a very nice source of heat. And it turns out about 1 gram of this plutonium-238 is sufficient to generate about half a watt of power, right? And that's obviously enough for all kinds of things. This is what a picture of a NASA RTG looks like for Voyager 1 and 2. And this is sort of a nice, cool image I found from NASA of all the different missions that have used the radioisotope-powered thermoelectric generators. Right? So this is also kind of interesting. So I think this answers the question that was asked a little bit earlier. You know, what's the relationship between the ZT and the efficiency, right? And my answer at the time was, you really need to match the internal resistance, the parasitic resistance of the thermoelectric generator, with the resistance that you're actually trying to drive. This is also true of solar cells. This is also true of pretty much any kind of circuit. At this point, this is basically a simple circuit, right? And so, of course, if you look at this, what I'm plotting over here is I'm plotting the voltage generated, which is called the open circuit voltage. Well, it's the open circuit voltage over there, but I'm plotting the voltage generated as a function of the current that is actually, flowing through this device, right? So the open circuit voltage is the highest voltage that I can get. That basically means I have no current flowing. However, as current begins to flow, right, the voltage will come down, right, basically just due to ohmic losses. And as the current increases, at some point, actually my voltage will go to zero, precisely when, the voltage divider between the internal resistance and the external resistance are essentially evening each other out. And so what you end up with is you end up in blue here, you have the actual power, the useful power generated by this thermoelectric power generator. And you can actually see that depending on what the construction of the thermoelectric generator is, depending on how much current I'm running on it, what the temperature is, and so on, there's actually really an optimal operating point. So the maximum power, in this case, happens to be extracted at a current of about 7 milliamps for this particular construction, right? So it's a very, very sort of, it has to be kind of optimized for the application, and you really want to operate it probably within a certain range. And within that range, my, best voltage is probably going to be on the order of about 6 volts. And of course, my current is going to be on the order of 7 to 8 milliamps or something like that. Okay. I'm going to talk, I think being at the GCEP symposium, you've probably seen this slide, at least 10, 15 times in the last few days. But, again, the reason I want to point out this is just taken from the Lawrence Livermore National Lab, just looking at the energy use in the US. Basically, my point is what's circled over here. About 60% of the energy generated in the US, of course, is lost as heat. This is something I'm sure other speakers have also mentioned, right? So 60% is lost of heat. It turns out 60% is about, if you want to put it in numbers, is about 15 terawatts. To me, I really work more with milliwatts and nanowatts in my research. So 15 terawatts is just such a mind-boggling large number that I kind of have to relate it to something. It turns out one giant power plant is about 1 gigawatt. And all the data center power consumption in the world, so all the data centers in the world are about 30 gigawatts. Right? And of course, these figures are growing because we're installing more and more data centers, but that's a completely different discussion. Nevertheless, we know that thermoelectric energy conversion efficiency is about 10%. Let's assume it's not even 10%. Let's assume it's 1 or 2%, right? So recovering even a few percent of these terawatts of heat lost in the world, right, would be huge, would be equivalent to many, many power plants, right? Would be many, many gigawatts of power. And it would be significantly larger than all the solar power that's installed, in the world today. Right? This, of course, is just sort of pencil and paper math. I mean, we know the math, the practice is obviously different, but just to kind of point out some really large numbers. So, again, this is again kind of a recap. I'm going to skip this really quickly, but thermoelectric for refrigeration, right? You use basically current flow to cool things down. My favorite example is small refrigerators for wine, cup holders or cooled car seats in certain fancier cars. And then, the opposite effect, which is basically using the temperature gradient to generate power. Again, used in car engines, which I'll describe in a moment. Also used in the Mars rover. Notice the newest Mars rover does not have solar panels because it has a source of plutonium for heat inside, and the source of cold is the Martian atmosphere. Not very warm on Mars most of the time, right? And the Mars rover basically roves around on about 100 watts of power, which is about 1/8 or 1/7, right, of a horsepower, but it's enough for this thing to call home. All right. Speaking of automotive applications, automotive automobiles are actually even more wasteful than power plants. I am told by people who work on these things that about 75% of the energy from combustion is really lost as heat. in the exhaust or the coolant, right? So the question is, can we recover some percentage of that? Of course, probably the most obvious place to stick a thermoelectric converter is on the exhaust manifold or on the catalytic converter right there. And so these things reach about 300 to 500 Celsius. Of course, the cold end is sort of the ambient air, right, where the car is. So we can actually harvest hundreds of watts using these things. And this has actually already been put into practice. I don't know if you can buy commercial cars using this. Certainly my car does not have this. Maybe some of you know better than I do. But certainly it has been done in practice, has been demonstrated. I think BMW has worked on this. In fact, this picture is of a BMW. It says right there, BMW Group, so I'm correctly citing them. Volkswagen has done some of this. And, you know, they can recover hundreds of watts. It's important to put this in perspective. 1 horsepower is about 750 watts. So they're not, you know, the car is obviously, you know, 200 horsepower or something like that, right? So it's not even recovering 1 horsepower. Less than 1% of the car's power is actually recovered. But it is sufficient to power something like the car radio or the air conditioner, right? And to essentially lessen the radiator, the alternator load in the cars, right? So it's kind of more, you know, maybe I should say it's done, you know, more sort of a nice thing to have. It's not really a requirement. It's probably not going to impact your gas mileage hugely, but it'll probably impact it by 1 or 2%. So, you know, it's a start. But these things are pretty much nearly commercial if they're not yet commercial already. I want to put things in perspective. I wasn't sure if I should put the slide all the way at the end or all the way at the beginning, so I stuck it, I guess, somewhere towards the end. There's a very nice paper called An Inconvenient Truth About Thermoelectrics. And you know, it has a catchy title, and he actually thanks Al Gore in the acknowledgments of his paper. I think maybe just for, I don't know if he actually talked to Al Gore about thermoelectrics or if he just, you know, thanks for ripping the title off. But regardless, what this person says in this paper is that, look, it's very important to put things in perspective and to realize that thermoelectric power generators will pretty much, does that mean 6 minutes or 50? Oh, that means 15 minutes. Okay. All right. It's like 2.5 minutes for each finger. Okay. Okay. So, all right, excellent. I think I only have about 5 or 10 more slides, probably five or 10 more slides, and these are pretty quick right now. So he basically says, look, thermoelectric power generators are not going to replace, you know, steam, power plants, right? They could make them more efficient, but they're not going to replace them. But it's very important to understand that thermoelectrics are really limited and maybe best suited for applications which are really not served by currently existing technology. That's really the way to think about these things, right? I don't want to stand up here and say, you know, these things are going to, you know, change everything. Right? They're not going to change everything, but they're going to change, they could change some things, and they already are. Wine coolers, car seats, USB, little thing, gadgets, right? Okay. That's more of a fun thing. I don't think it really, like we said, doesn't really cool my drink or heat my coffee too well. But it's fun. So, you know, again, the important thing is it seems to be that small size applications are actually benefiting the most from this. So again, that's where, you know, the cup holder that is being cooled is a good thing, right? You're not going to stick a refrigerator with Freon inside your car to actually just keep, you know, a cold can of you know, Sprite or Coke or whatever you're drinking in your car, right? Also, sometimes you need to cool a laser or a photodetector or something like that, right? In fact, in my lab, we have photodetectors used in a big microscope, which are actually thermoelectrically cooled, right? There's no way to fit any other kind of coolant inside that dimensions that are needed over there, right? Certainly waste heat recovery, I've already talked about that quite a bit. Certainly another thing that I think is you know, I want to point out is we should not just fixate on ZT. So a lot of people I feel that are talking, they're just, you know, they're sort of, this is the efficiency is basically the ZT, right? From a practical point of view, cost per watt is also important, right? So sometimes, you know, maybe it's okay to have a ZT less than 1 if the material actually is relatively inexpensive, right? You might be able to actually more broadly adopt it, right? And this is kind of what's forcing many groups, or not forcing, but encouraging many groups, including mine, to look at thermoelectrics based on polymers. Even though the efficiency is lower than traditional semiconductors, polymers are actually cheaper than crystalline semiconductors. And similar things have been happening in the solar cell community, right, where people have been talking about polymer solar cells, which have lower efficiencies, than silicon solar cells, but they're probably cheaper, so they might be more widely adopted more quickly. And of course, if you think about power generation in remote places, I already mentioned outer space. I mentioned lighthouses in the edges of northern Siberia, places and communities without power plants and electric grid. Certainly, thermoelectric modules in cooking stoves and solar thermal systems actually could be very, very impactful. They would really change the quality of life for millions and maybe even billions of people. I mentioned a little bit about cost, and I do also, this is not really an economics talk. I'm not an economist, so I'm not really an expert on cost issues. I did provide a couple of cost-based analyses at the end of the handout. But I do want to mention a little bit about cost. So, for example, bismuth tellurium materials, they're pretty expensive. They're about over $100 per kilogram, right? They're expensive because they're rare. They're also toxic, right? So that's not fun. They also tend to be brittle, which means you can't really bend them nicely. So you cannot put them in a bunch of applications that maybe bendability would be important, right? So again, this is where polymers, like P.PSS, very, very inexpensive materials, right? And polymers, in a very sort of fun twist of nature, I guess, or of fate in nature, polymers already have two of the properties that are relevant for thermoelectrics. One of them is they have extremely low thermal conductivity, and conductant polymers have reasonably high electrical conductivity. Not as high as the semiconductors, but reasonably high, right? So the challenge recently has been to use maybe nanostructuring, which I mentioned earlier, such as, we're in my group, we're looking at using nanostructuring to essentially increase the Seebeck coefficient of these polymers, which are basically already known and already existing for other applications. Right? The bonus thing that we get from polymers is that they're basically mechanically flexible, and some of them are actually solution processable, right? So that would also keep the costs quite low, and having mechanically flexible polymers, as one of my colleagues likes to say, it allows us to put these pictures with the obligatory gloved hand, flexing these things, right? So you'll see a lot of people working on flexible things, they'll have this picture of the blue gloves, bending whatever they're working on. Okay. Speaking of cost, I have another plot that I like to share with you. This is a plot showing the abundance of the atomic elements in the Earth's crust. I took this directly from the government website, which is also on Wikipedia, basically. The reason silicon is so dominant in semiconductors is because it's the #2 most abundant element on Earth. I used to work at Intel, and I used to joke with my colleagues that if Intel could build chips out of oxygen, they would, because it's just slightly more abundant than silicon in the Earth's crust, right? But alas, oxygen is not a semiconductor at room temperature. It's a gas, so we can't really build chips out of it. Silicon, on the other hand, we happen to live on a planet that's mostly made out of silicon. So that really keeps our processors and our computers and our gadgets and everything else pretty cheap. Silicon is not a good thermoelectric material by default, but people have found ways, as I mentioned a little bit earlier, using the nanostructuring and the nanowires to increase its thermoelectric appeal, right? So of course, something based on silicon, or maybe even based on carbon, which is another relatively common material on Earth, would actually automatically be made from a fairly available material, right? If you start thinking about abundance like that. On the other hand, if you look at the materials which are making up thermoelectrics today, germanium, antimony, tellurium, lead, bismuth, not only are they rare, right, they're also toxic, but they're rare, which basically means they're very, very expensive. And I am told that, these materials occasionally get into the middle of, big geopolitical battles between countries. Some of these materials may only be stored in a certain, ore in a war-torn region of the world. And so this is also obviously putting pressure on prices. So there are other incentives besides efficiency and so on, to move away maybe from some of these materials like tellurium, bismuth, and antimony. Unfortunately, these are all the ones that are inside the thermoelectrics I passed around today. Okay. Some other more fun topics, maybe on the topic of, or related to these flexible materials. A couple of years ago, I read a paper. This paper actually came out in 1996 already, so it's been a while. But a couple of years I read a paper that really motivated me to start looking into this. And it turns out, if you run the math, you can actually harvest enough energy from the human body to power small electronics, maybe sensors, maybe even something like a phone. Not enough to power a laptop, it turns out, but enough to power a small phone, maybe sensors. how does the math work out? So, let's look at power consumption. So, desktop PC about 100 watts, a notebook PC about 10 watts, microchips, sensors, microwatts to milliwatts. So that's good to know. The human body at rest, so all of us, more or less, sitting here right now, we are generating about 100 watts worth of heat, nonstop, right? I was reading somewhere that Usain Bolt, when he runs the 100-meter dash, he's burning kilowatts of power. But most of us cannot really break the 1 or 2 kilowatt barrier. And when we sit around, this is it. So about 100 watts. That's it. Okay. Which is interesting, right? I mean, even Usain Bolt, if you think about it, right, he's running at like 3 or 4 horsepower. That's basically it. That's the maximum power that the fastest human on Earth, produces. The rest of us are sort of running at fractions of a horsepower, basically. Okay. So it's kind of interesting to kind of think about what can you do with this heat from the human body. So you can calculate what the efficiency of harvesting energy from the human body, thermal energy from the human body is, by looking at what's called the Carnot cycle. That sort of gives us an upper thermodynamic limit. Temperature of the body minus temperature of the ambient divided by the temperature of the body, it means it's about 5% efficiency, right? So that means that if I were at the Carnot limit, which is the fundamental thermodynamic limit, I would be able to harvest about 5 watts, 5% of about 100 watts, if I was able to actually harvest energy from my whole body, which of course would be uncomfortable, but it's nice to know what the upper limits are. Now, I have to multiply that by about 10% efficiency for modern thermoelectrics, which we discussed earlier, depends on ZT, and so on. And so now I know that using modern thermoelectrics, I can probably harvest about 0.5% from these 100 watts. The numbers work out very, very nicely. That's about 0.5 watt, right? So 0.5 watt is actually useful. I wrote here 0.5 watt to 5 watt because I was talking about sort of what the body heat is, but really I can really only harvest sort of the lower end of this, which is 0.5 watt, right? But 0.5 watt is nice to know because 0.5 watt means that, okay, I cannot power my PC, I cannot power my tablet, probably, right? But I can power small chips, right? Small chips are sensors, small chips are watches. For example, as early as 1998, the Japanese company Seiko already was manufacturing a watch that was entirely powered by body heat, right? It's the Seiko thermic watch, came out in 1998. It was simply powered by the heat of the wrist of the user, right? In 2002, in the UK at the Glastonbury music festival in the UK, they were passing around apparently one of the UK cell phone carriers as a marketing stunt, passed around these boots. And when I first saw the press release for this 2 years ago, I said, these must have been mechanical piezoelectric generators because these people were dancing, right, at the music festival. If you actually I read the release a little bit more deeply, and I realized these were actually thermoelectric power generators. So basically, the heat was coming from the foot inside of it, and then the cold was basically the sole, the cold British mud underneath the boots, right? So they were they were passing these out, and apparently people could use these things to actually charge or recharge their cell phones at this music festival. So these things actually do exist, and that's just from the human body. So, this is not really science fiction. It's actually kind of fun to think about it. But of course, there's lots of practical challenges, as I mentioned earlier. Practical challenges with unappealing names like thermal grease. So, watches and boots already demonstrated, and we can actually calculate the maximum power that we can harvest from the skin. We can harvest just below, or let's use round numbers. We can harvest on the order of 100 microwatts per square centimeter. That's assuming, of course, I have the full temperature difference between the skin surface and the air. And of course, I cannot harvest nearly as much in warm countries like Singapore, but I can do it better in countries where the ambient temperature is lower. Certainly would work in the Bay Area and certainly would work indoors, right, in this room where the temperature probably is around 22 Celsius. However, there's very, very many challenges on these things, right? So these challenges are not really fundamental physics. They're actually just almost manufacturing related. And a lot of these things have to do with minimizing these parasitic losses between the heat transfer between the skin and the thermoelectric, and then see right here is temperature of the skin, and actually coupling this really well, and then actually also minimizing the thermoelectric, minimizing the thermal resistance between the thermoelectric generator and the air, right? And in some cases, you actually really need a little bit of a heat sink on these things, right? Which is maybe not necessarily so appealing visually, but people have played with this, and students in my lab are actually playing with exactly these kinds of things right now, seeing how they can optimize these kinds of generators. All right. So I probably only have 1 or 2 more minutes. The final remarks part of the talk was basically really just a little bit more selfish, kind of, some of the areas that my group works in, also hinting at some of the sort of the research challenges that we face, some of the things that are maybe a little bit farther away from commercial applications, but nevertheless very, very interesting to think about from a research point of view. I come from the Department of Electrical Engineering. And generally, we tend to think about electronics. Of course, we're electrical engineers, but we tend to think about electronics in the context of power and heat. And I love this picture because, all of us have heard of the IBM Watson, the Jeopardy champion. But what IBM didn't tell you is that the human brain of these 2 competitors was operating at 20 watts, and their machine was operating at 200 kilowatts. So the game was very much stacked against the humans by a factor of 10,000, right? This is highly inefficient way to play Jeopardy, but nevertheless they sort of powered through it. And we're also all familiar with conventional Moore's law scaling, right? Moore's law basically says, hey, if I make things smaller, they're going to get faster and more energy efficient. But we all know we're so close to atomic dimension in electronics that we could probably only maybe improve things by a factor of 10 in size, speed, and power, right? So there's a huge need thinking about how do we go beyond Moore and sort of try to think about electronics in the context of power harvesting, and sort of power management. So this is exactly what we do in my research group. We basically work on what I like to call 2 sides of the same coin. One side is basically lowering the power at its source, right? So trying to design lower power devices, transistors, memory, interconnects, and so on, sensors, right? And on the other side, we realize, look, no matter what we do, computing will always generate some amount of power, so we have to learn how to deal with that. And also because we're humans and we live in moderate, climates, we live at 300 Kelvin roughly, there's always going to be thermal gradients around us, such as between our body and the environment. So how do we manage and maybe deal with some of the heat and some of these temperature gradients that occur around us? Since we're academics in my group, of course, we usually seek to get a fundamental understanding of things, and I try to pepper my talk with a bit of fundamental sort of references. I'm sort of trying to understand what are the maximum or minimum limits of what you could do if you could really push physics to its limits. But since we're also engineers, of course, everything that we do is ultimately connected to something that is a practical application. We don't necessarily we do a little bit of science for the sake of science, but most of the science that we do is really for the sake of applications. This is what I call it. Whenever I have a visitor in my office, I usually show this one slide. This is sort of everything that we do on one slide. We have a website, poplab.stanford.edu. And again, a lot of the motivation has to do with these power density issues in electronics. CPU power densities have been rising exponentially, in fact, over the last 20 years. And we've pretty much been flattened by power and heat issues for the last 9 years. We really cannot run CPUs any faster right now because we don't know how to get rid of the heat, right? So that's kind of the power supply side or the heat supply side, right? I teach a course right here at Stanford that I just started this fall called Energy and Electronics. And actually, a lot of the slides that I showed you today are slides that I share with my students in this course as well. The course is, of course, not focused on thermoelectrics. It's focused more on the fundamentals of energy and nanoscale electronics. But there's a lot of overlap. This is really based on our research. And some of the things that we work on, I already talked about energy harvesting from the body up to maybe a watt or a fraction of a watt, maybe, right? So this is one of the things that we work on. But we also work on other materials. We work on 2D materials. Graphene is probably the most well-known of them. Graphene by itself does not have good thermoelectric properties, so we're not looking at it for graphene. We're looking at it for electronic applications. But there are other materials like MOS2, which is also a 2-dimensional sheet and actually does have good thermoelectric properties, it turns out, and we're actually doing those measurements right now. So there may be ways to compare these things, to combine these things to create actually even thermoelectric applications, such that this bubble and this bubble, these 2 regions, essentially, I should show them as overlapping. I should probably show these as overlapping as these is overlapping as well. In fact, all of these, right, are sort of overlapping, but I show them as separate regions over here. And then we work on the sort of power supply side of electronics. A few years ago, we've demonstrated, for example, data storage using 100 times lower power per bit that it is possible to achieve, or that had been possible to achieve until then. So this was a fairly nice leap. Moore's law, for example, gives us a factor of 2 maybe every few years. we actually demonstrated is it possible to get a factor of 100 just by changing the materials that you're playing with a little bit and basically changing the dimensions. And so we've demonstrated some really low power data storage, which of course becomes a big issue in data centers, right? If you could actually replicate this at the scale of a data center, you would actually have significantly lower power consumption in data centers, which would translate into gigawatts of power worldwide. I don't really want to spend too much time describing. This is really sort of a fairly detailed technical discovery, and you know I'm actually running out of time. But the reference is listed over here, and I think I linked it at the end as well. These are some fairly detailed measurements where we've actually measured thermoelectric effects inside our transistors. These are graphene transistors, and it kind of struck me as funny that, as I mentioned earlier, graphene transistors are not even, or graphene is not necessarily even a good thermoelectric material, yet these things were measurable, right? So if we actually play with materials that actually have better thermoelectric properties, we might be able to actually design transistors that have built-in thermoelectrics. This is something that's never been done, at least not deliberately. This was almost an accident, even this measurement over here. It was almost an accident. But thinking about electronics that actually have, you know, do an electronic function like compute, you know, some code or something like that, right, or store data and so on, but also somehow are able to manage their own internal heating is something that we're trying to do. And of course, there is no free lunch. It's not like we're actually, you know, getting completely rid of the heat. We're actually just moving it away from the regions where the heat would be most damaging to the reliability or to the otherwise well-being of these devices. I mentioned these layered materials. I've become really interested in these layered materials partly because I've been teaching some of these thermoelectric concepts. As I mentioned earlier, using these super lattices actually really helps block heat flow. Well, it turns out graphene and other 2D materials can actually be stacked naturally into super lattices. You know, you can actually, we've done this in the lab. This is a picture from our lab of, it's kind of hard to see probably in the back, but here we've layered 10, you know, we've taken apart graphene and then we've layered it back together at varying angles. And it actually turns out this has an astoundingly low thermal conductivity, right? We're now measuring the electrical properties to see if there's actually something interesting there, but the thermal properties were extremely low. In fact, it had a thermal conductivity comparable to air, which is very, very remarkable for an otherwise solid material. And this can be achieved with other layered materials as well. It has been demonstrated in tungsten diselenide, which is sort of an interesting material. Although tungsten diselenide is not a good conductor of electricity, so would not necessarily make a good thermoelectric. So that's that. But some of these materials have favorable properties for thermoelectrics. And so here, sort of, this is what I call a PowerPoint device or PowerPoint science, right? We haven't really built any of these things yet, but these are things that we're pushing towards building. This is sort of where a lot of this research, and certainly in my group, is heading. Is I mentioned earlier, trying to build transistors or memory elements with built-in thermoelectric coolers. Heat spreaders, I guess that's probably the more sort of obvious thing. We're done. Okay, I'm done. And then obviously, you know, talking about thermoelectric coolers on flexible substrates, I think is actually a very, very interesting thing, because flexible substrates tend to be things like plastics and fabrics, which by definition have very poor thermal properties. So this is really my last two slides. You know, I made a joke, or kind of a joke, but it's really a serious issue, about the IBM Jeopardy champion being 10,000 times more energy inefficient than the human brain. And I also talked about data centers. So what if, you know, somehow we were able to reduce all the energy of data centers in the US by a factor of 10,000? That's roughly the power of two of these fancy sports cars, about 1 megawatt, right? These are still kind of large numbers. If we are able to take something like a smartphone and reduce its power consumption by a factor of 10,000, hypothetically, please don't take this seriously. I don't know how to do this. But if we, you know, if we were to do this, then we would reduce this down to 5 microwatts, which is the power of a watch, which we know to power by body heat today. Realistically, I think probably what's going to happen is, or what I hope is going to happen is we're going to meet in the middle. I think that those of us who work on, you know, purely making electronics more energy efficient will continue to do so, right? And will reduce the energy consumption of electronics, right? But at the same time, I think it's very, very important to kind of bring up the power supply side, right? From all the clever ways we can, whether it's body heat, whether it's vibration, of course, solar, which was not the topic of this talk, but certainly is there as an option, right? So I really think, hopefully, we will meet in the middle. So hopefully I'd like to say maybe in a few years, we will have body-powered gadgets more than just a watch, right? Sensors and so on that communicate with our smartphones and so on. And so really to summarize, I'm, as a researcher in this field, not necessarily as not in the thermoelectrics, but in the broader field of thermal energy harvesting, as well as low power electronics, I'm still interested in Moore's law, but I think it's slowing down if hasn't completely stopped. I think it's still working, but it's slowing down. But this is what I'm really excited about. I'm really excited about the fact that we can think about energy within the context of electronics. And I really think that there are opportunities for much, much greater than 10x factors of improving efficiency. And it's really a convergence that I'm excited about of low power electronics, energy harvesting, of course, which is what most of this talk was about, as well as novel nanomaterials, which also a good chunk of this talk was also dedicated to. And while we're doing this, I think certainly as an academic, but also as a well-educated human being, I'd like to know what the fundamental limits are, right? Without knowing what the fundamental limits are, I really don't know what to aim for, right? I really want to know, hey, this is not going to get any better than this. So then I know that if I read a paper that's exceeded that, they probably made a mistake, right? And so it's kind of nice to know these things. And in some respects, we are approaching fundamental limits. In some other respects, as I showed today, we're very far away from them. These are the references that I collected most of my materials for today. I included, I will share the PDF, by the way, after the talk. So these are all clickable links inside the PDF. So you don't have to type them in. But they're written inside the handout that you received. By the way, if you did not pick up a handout, are there any extra handouts left? Okay, thank you. So they're next to Sunny in the back. And I think I'm out of time, but I'll be happy to stick around for a few minutes to answer more questions. Thank you.